So in this video, we're going to talk about collecting evidence to justify your model. So if you want to use a linear model or an exponential model, it's good to have evidence to decide whether or not that's the correct type of model to use. So that's what this video is about. So to do that, we need to understand the concept of rate of change. And in general, we consider the rate of change between two variables, y and x, as this delta y, or the change in y. This Greek letter delta means change, divided by delta x, or the change in x. You might recognize this as the calculation for slope or gradient of a line. It means the same thing. The only difference here is that we can use rate of change to talk about functions that are not straight lines, like this curve here. Okay, so just to do a quick recap of slope calculations, rate of change we can calculate between any 2 points. We can find an average rate of change. So for example, in this graph here, on the linear appearing graph, we can choose a bunch of points along that graph, 1 point, 2 points, 3 points, 4 points, and we can find the rate of change between each of those pairs of points. So for example, from this point to this point, the change in y is this increase, which is, it's going up by 2, so change in y is 2. And here the change in x, we're moving to the right 1 unit. So the change in x is positive 1. So change in y over change in x would be 2 over 1, which simplifies to 2. You notice that if you went between these 2 points, the change in y here is 2, the change in x here is 1. So when we calculate the rate of change between those 2 points, we get the same answer. And actually, between these 2 points, we get the same answer as well. This is the whole concept of a linear function. It's the fact that the rate of change is constant. Here the rate of change is 2, here the rate of change is 2, and here the rate of change is 2. So that's what we're looking for when we're looking at a linear model. For an exponential model like this one, this appears exponential. If we want to calculate rate of change, again, we need to choose a bunch of points along that graph. So here I've selected some points, here, 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 and here. And as you can see this time, I'm increasing the x's by 1 each time. This is 1 unit long. This is 1 unit long. And as you can see, the increase in y is changing this time. So this one's going to be a little bit different. For these first 2 points, the change in y is plus 1, and the change in x is plus 1. So the rate of change is 1 over 1, which is equal to 1. So between these 2 points, the rate of change is 1. If you look between these 2 points, now the change in y, to go from this point all the way up to this point, takes 2 units. So the change in y is 2 units, which gives us 2 over 1, or a rate of change of 2. Let's take these final 2 points. So between these 2 points, delta y, the change in y, is 4, because from this coordinate to this coordinate, we have to increase the y coordinate by 4. And change in x is still 1. So the rate of change is 4 over 1, which is equal to 4. Now, if you look at these numbers carefully, 1, 2, 4, you'll notice a pattern. You should notice that those numbers are doubling each time. So when we have a rate of change that follows a geometric sequence, That's a situation when we are looking at an exponential function. So let's take a look at a couple examples. This one we are looking at the United States confirmed cases of coronavirus. We're looking at total cases right now, so not the amount of daily cases, the total cases. And to smooth this out a little bit, I'm going to use the 7-day rolling average, just so that we get a little bit of a smoother curve. So if we are looking at this graph, you will see that some parts of it, like along here, it's a bit curved. So this, you might think this is an exponential function. We're not going to look at that right now, because what I'm more interested in is this long stretch of graph here, which appears to be linear. If we want to show that it's linear, what we want to do is show that the rate of change is constant through that period. So let's take a look at these numbers a little bit more closely. If we want to zoom in on this area here, we can change the dates. So I'm going to change dates. So when I'm looking at this graph, I see a curved area sort of around here. And what's I think is interesting is that looks like it's not exactly clear where it stops curving, but looks like between days 40 and 60 we have quite a straight line. So I want to look into this in more detail. So let's check out those numbers and see if we can find a constant rate of change. Okay, so I've just taken a picture of that and have written the numbers here so that they're a little bit bigger and so that you can see. So I just picked 5 days in a row starting from April 17th. And if we want to find a constant rate of change, in this case we're going, our delta x, or our change in x, is just 1 day each time. So that's kind of handy because we're just dividing by 1 every time. So all we need to do is find the difference. It's like finding the common difference of an arithmetic sequence. So the difference between these two numbers is what you get when you subtract the bigger one from the smaller one. You get 28,658. If you do that with the next two numbers, you get 29,305. With the next two numbers, you get 28,874. And then with the final two dates, we get 29,308. So what you will notice if you look at those numbers is they are all very, very close to each other. They're all right around 29,000. They're not exactly the same, but that's probably to be expected because this is data from the real world. The real world doesn't work in clear arithmetic sequences very often. So this is some good evidence that we have a linear graph here because the rate of change is almost constant. All of these numbers in terms of rate of change are almost the same number. I'll give you a little bonus method for checking this using that website. We can actually look at the daily new cases, and that can give us a really good hint for whether or not the growth might be linear. Okay, so I'm back here at this graph. One thing I noticed is the x-axis before was counting in the number of days since the 100th confirmed case. I prefer to change that actually so that I can see the actual dates because I'm not comparing countries right now. I'm just looking at one particular country. So if I uncheck this box, now it actually gives me the date down here and we can look at individual dates. So, like I said, we looked in this area here and it looked linear, and I said I was going to show you a little trick to identify that. If we instead of looking at the total cases, if we look at the daily new cases, we see something pretty interesting. So on these dates we were going from early April to mid-April to the end of April. What you'll notice is this graph is almost flat here. And what that means is the amount of new cases each day is almost the same day after day. So in this case, when we're looking at the daily new cases, the change from one day to the next is actually represented exactly by these numbers. So when you have a flat or sort of horizontal graph with daily new cases, that means you're getting the same number of new cases each day, which is exactly what gives us that constant rate of growth, or a linear function. So this is a good little clue to look for if you're trying to identify linear growth. Okay, and finally, we are going to look at exponential models. So I've switched to the country of Brazil now. I'm going to change this to total, so we look at the total number of cases in Brazil. Confirmed cases. And this is a nice example to use for data purposes because it does really resemble an exponential function. So because we're trying to model this as an exponential function, and if we want to collect evidence for why it might be an exponential function, we need to take those days one day at a time and see if we can find a common ratio. See if we can find some kind of growth rate. So I've collected some data for some days in April, that around this curved part here where I said I suspected that it's an exponential growth situation. And I just took these numbers straight off the graph. Again, if we think it's an exponential function, then we should be able to find a constant ratio, or you can think of it as a growth rate from one term to the next term. So it's like a multiplier, right? So if you want to find what that common ratio is, we have to divide one term by the previous term. So for example, between these 2 days, 25th and 26th of April, we need to divide 613,256 by 584,598. And if we do that, we get a multiplier of 1.071. You can think of that as 7.1% increase. We can do the same with the other days, and what you find is these numbers here. Again, these are all not exactly the same, but they're all very close to each other. So that suggests that if we wanted to make an exponential model, this data would be appropriate for that, because all of the multipliers here to get from one day to the next day are quite close to each other. Okay, so that's one way to show evidence that the data that you're looking at could be modeled using an exponential function. If you've made it this far in the video, I've got a bonus method for you. It's called doubling time. So this is another way that you can collect evidence that the data that you're looking at is appropriate for an exponential model. And not only does it do that, but it helps you understand the concept of exponential growth a little bit better, and helps you get your head around the numbers a little bit easier. So it's called doubling time. Let's take a look at that quickly. All right, so we're back with Brazil here. And the concept of doubling time is exactly what it sounds like. It's the amount of time that it takes for something to double. If we have exponential growth, if we have exponential growth, that means that the doubling time should be about constant. Okay, so doubling, let's see, I just want to get a nice number to start with here. So this is about 20,000 here. So the doubling time would be the time that it takes me to get from here to about 40,000. Just to make the numbers rough here. So I'm going to count the number of days that it takes to get to 40,000 from here. 1, 2, 3, 4, 5, 6, 7, 8, 9 about. So about 9 days was our doubling time. Okay, now let's check to see how much time it takes for the next doubling to happen. So it took us 9 days to double from 20 to 40. Let's see, to go to 40 to 80. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, it's closer to this day. So again, it took 9 days approximately to double. We could go one more and see if it keeps working. So let's see, we want to go now to double. We're going to 160,000 roughly. So counting days, we get 1 day, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 days. So that doubling time took a little bit longer. So we had 9 days, 9 days, 11 days. Those were our doubling times. Now, because those are all very close to each other, that's more good evidence that we have exponential growth in this situation.